For centuries, humans have measured time using moving parts, pendulums that swing side to side, mechanical clocks ticking with gears, quartz watches that hum with vibrating crystals. And although precise, the parts they are made of can wear down over time, and the time they capture can drift. Even the most advanced can lose seconds a year. That might not seem like much, but when you are navigating satellites, running global financial networks, or synchronizing data across the planet, a single second can make a world of difference. In a search for a truly universal and reliable way to measure time, scientists turn to the steadiest timekeeper in nature, the atom. Electrons and atoms have a built-in tick, a vibration that never changes, regardless of the atom's location. In other words, an atom here on Earth and an atom on the other side of the universe will tick at exactly the same frequency. That makes atoms the perfect reference for keeping time that never wavers.
Now, conventional atomic clocks tend to use cesium atoms because they come with a remarkably reliable internal tick. Inside these atomic clocks, a beam of atoms passes through a field of microwaves. The same microwaves actually used to heat up food in your kitchen. Microwaves are used to provide energy to the atoms, causing them to change their energy state from low to high. This change occurs only when the microwave frequency and the atomic frequency are in tune, signaling that everything is locked in. Then, by counting the number of microwave cycles that cause this change of energy, the clock can define a second.
Without atomic clocks, our modern world simply wouldn't work. They keep GPS accurate within centimeters and ensure that financial systems, communication networks, and devices worldwide stay perfectly synchronized, right down to the timestamp on your phone.
The most advanced atomic clocks today won't lose a single second for longer than the universe has existed. But we and other scientists are constantly refining and chasing even more perfect time. In our lab, we work with an atom called ytterbium, which has a more reliable built-in tick than cesium. Also, importantly, ytterbium ticks nearly 60,000 times faster than cesium, which provides a more precise way to measure time. In principle, the ytterbium clock is very similar to the cesium clock, but instead of the microwaves, we use lasers. At present, such optical atomic clocks are so big that they occupy a whole room. But we and other colleagues are developing more robust systems that could be portable. These optical atomic clocks will further improve global positioning systems, allowing us to track fast-moving objects, such as rockets in space, with much greater precision. The sensitivity of such devices to the surrounding world is mind-bending. It could allow us to probe the most elusive phenomena, from predicting the earthquakes based on changes in the geometry of space-time to measuring new fundamental forces between the constituents of the atom.
A clock precise enough to keep perfect time for billions of years could not only safeguard modern systems, but also sharpen our understanding of physics, space, and time itself.